My talk start at 3:15 or at 3. Who is in charge?
Hello, good afternoon, everyone. Hello.
Hi.
Hi, Dr. Ravi. Can you hear me, please?
Yeah, we can see.
Hello, good afternoon, Dr. Ravi, and our colleagues and our trainees. Today, I will host a session 4 on behalf of Professor Joe. In Professor 4, there are two topics. One is from Dr. Pravi Sakur from Water Resource Department, India Institute of Remote Sensing. And the other one will be from Professor Yuki Chanchi from the University of Tokyo. Now, are you ready, Dr. Perry?
Yes, I am ready.
Okay, now please. Thank you.
Yeah, I will share my screen. So my slides are visible?
Yes, sir.
Okay, I'm just moving to next slide. Is it moving?
Yes, sir.
Okay. So thank you, organizers, and especially
Cannot hear you.
Hello, Dr. Previ. BBC.
hello.
Yeah, it's good now.
Okay. So I will be briefly talking you about role of geospatial technology and its application in surface water resources and flood forecasting. So I am Dr. Praveen Thakur, head of water source department at Indian Institute of Remote Sensing, Dehradun. So this is the brief outline, just a few introductory slides on basics of remote sensing, GIS for water monitoring, what are the various global Earth observation systems which are in place to monitor the water sources and how we use it for monitoring the surface water sources and the hydrology. And I'm just switching off my video so that connection is stable. So then the role of remote sensing GIS for estimation of hydrological cycle variables and then flood mapping monitoring using remote sensing, and how this remote sensing GIS, GNSS, they combinedly provide you information for hydrological modeling, including your flood modeling and forecasting, and what are the future missions from the Earth observation satellites which will help us in this particular regard. So if you see the global distribution of the rainfall, which is the main trigger of the floods and also the water availability. So the amount of water available will derive what kind of agroecological zones or what kind of agricultural practices are there. So you can see here the India, Southeast Asia, and some parts of Africa, Amazon, and some parts of the Europe, Eastern Australia. So they do receive very heavy annual rainfall, and any excess rainfall will lead to the flooding. And also depending upon at what point of the location you are located, whether you are near the mountains or near the just below the floodplains or near the coastal area, your water demand and agriculture and other water needs will be different. So remote sensing help us to identify and map all these spatial and temporal variability. And as I told, this precipitation, if it is in optimal amount, it will be very good. Otherwise, if there is a deficit, leads to the drought, and if it is in excess, it leads to the flooding. And from the water use point of view, it is the agriculture sector which is the main water usage, followed by domestic and the industrial water use. And for the India and other many countries in South Asia, we have the monsoon, where the 70 to 90% of the rainfall happens in 3 months or 3 to 4 months time. And if you see the basic fundamental of the remote sensing, so surface water, liquid water, it will have very less reflectance in the multispectral domain. Very most of the energy gets absorbed, and this is for the vegetation, this is for the soil. And it is a reverse case for the snow, where you have the very high reflectance followed by absorption in the near infrared, this middle infrared, and the shortwave infrared 1.5, 1.9, and 2.4, whereas clouds will have the high reflectance. So this is one example of the Chandra glacier. Here we have the glacier lake here, snow having high reflectance. This is the cloud in the white shape, and then we have this one reservoir, Hiri reservoir here, where we have the surface water here, which can be easily seen here. Then we have different remote sensing. This is applicable for not just for India, China, or any space agency like ESA or US. So this is applicable to all. So we have the geostationary satellites, which gives us the very good information about the dynamic processes like the meteorological observations. Every few minutes you can get it. Then the high medium resolution, the LEO orbit, we have the multispectral radar and the scatterometer data sets in the LEO orbit. And then we have this UAV and the drones, which gives us very high resolution, large scale maps on the particular region or area at very high precision. So from few minutes to number of days repeativity, from few centimeters to few hundred meters. So this resolution changes, and there are various applications of remote sensing. So if you see how we combine what we want to do here, we want to represent the real world in terms of the virtual world. Sometimes the one terminology has come, the twin earth. So in field of water sources, we want to simulate what is happening in a watershed by combining my meteorological inputs like the climate, weather, like rainfall, temperature, which is having very high variability in space and time. And then we have the thematic or the land surface attributes like your digital elevation model, the land use, and other surface water features, which will have the spatial variability, but not as fast temporal variability. And if you add those raster data sets, vector data sets, you can represent the real world in GIS. And if you add the time factor into it, you can do the modeling also. So this is the summary here. So here you can see the full from 1970 onwards, whether it is reservoir, lake, or your village pond, or if it is large scale flooding, remote sensing will be able to map it and monitor it at continuously. Then if you are living in a mountainous region, you have the seasonal snow, that seasonal snow cover depletion, glacier mapping can also be done. If you have the precipitation, the satellite based precipitation is very frequently used by many researchers, and it is being augmented to the traditional rain gauges and the Doppler weather radars. Then you have this evapotranspiration using the thermal data, NDVI and LAI, which is being used to estimate the water demand. Then you have this soil moisture combination of active and passive, which gives the soil moisture. And most importantly, the topography, the digital terrain models, DM models, which gives us the river cross section, the general topographical information. And you have this water demand. If you know from the remote sensing data, you can know the crop water demand, this crop water acreage. From the crop water acreage, using the crop coefficient or the other data sets, you can estimate the irrigation water demand. And also, if you want to plan a new city or new town, or you want to augment the water supply scheme, so you want to have the location of the water bodies. So the identification of drinking water sources is also possible using this medium to high resolution remote sensing data. So this is just a summary here. where I am showing this Dehradun city, which is actually sitting on the ridge line. Water to the west, it will go to the Yamuna River, and the water to the east, it will go to the Ganga River. And this is the Black River. This represents the watershed boundary here. So you can see the spatial variability. You have this moist deciduous, you have this agriculture area, and then you have this ephemeral rivers, and then all this hydrology multi-scale can be easily mapped using remote sensing, and then this using land use, land cover map, soil map. You can do the hydrograph estimation, hydraulics, river hydraulics, or the urban city areas that can be modeled to estimate the design flow or the flood flows or the water availability. The length, area, volume of the water sources can be estimated. And if you have the hydrogeological maps, you can do the combination of surface water and groundwater. And if you have the crop area acreage, crop coefficient, and the evapotranspiration data, it will be directly helping you for the irrigation water management. So this remote sensing GIS is integral part of any water studies that we do these days. And then this is just example of reservoir Tehri Dam, which was under construction in Bhagirathi and Hilangna River. And this is before the construction, and this is after the construction. You can generate the area, volume, elevation, capacity curve using a digital elevation model and the design parameters of the dam. And then you can use this data for estimating the reservoir sedimentation. So this is available for all the countries. Surface water resources freely available in the Google Earth engine, and also if you want for the India, you can use water body information system of India to map and download all the water bodies information in case of our case, or if you are using the global data, you can use the Global Earth Explorer. So this is one example of reservoir sedimentation, which is operationally being done by the Central Water Commission. So from the satellite data, you get the water spread area. From the ground observation or the altimeter observation, you get the water level height, and using the trapezoidal formula, you calculate the capacity of the reservoir at particular time. And if you add with the base capacity, you get the cumulative capacity. So many of these reservoirs are more than 50 years of life. So these 50 years, lot of sedimentation comes. So they reduce the effective volume. So once you calculate the present volume, the difference between the last survey and the present volume will give you the area which is reduced due to the volume which is reduced due to the sedimentation into the reservoir. Then this is the water quality. This is the Modi's data of Ganga and Brahmaputra river confluence. This is Bangladesh here. So if you have more suspended sediments into the water, it is more turbid, it will scatter more. So this is just a hyperspectral lab-based spectra. This is for the clear water. This is for the silt, where it has been added 1000 milligrams per liter. So you can see increase in the reflectance. And using this information, there is a direct estimation of turbidity, which you can estimate. And during the 2020 this COVID lockdown, when we had in India, so a lot of human and industrial activities stopped for almost 1 month. So there was natural regeneration of the water quality, as seen in this Sentinel data sets. There was a decrease in turbidity because water availability was more in the river. No industries were polluting. So you can see in Haridwar and in here in the Prayagraj area, in the Kanpur area, there is an increase in the water quality by satellite data observed from the Sentinel-2. So this kind of studies can be done. And then one important study which is done is for the project implementation. Before the construction of the water conservation or the flood control structure, what was the condition? And after construction of the dam or the check dam, you can see increase in the agriculture area, decrease in the flash floods in this particular watershed. So this is very effective way of monitoring the your project activities. Then to get this data for India, we have this India WARIS, Water Resource Information System, which was combined project of ISRO and Central Water Commission. Now it is fully funded by World Bank, and the full digital database is there. And then there are some other sites also, like World Resource Institute, where a lot of data set on the surface water, water supplies, water points. It is available for developing countries, for example, for African countries I have shown here. Then you have this global lakes and wetlands level 1 to level 3 data sets on the lakes and wetlands is available. Then you have this FAO Aquasat, where the global information system for water and agriculture is there in the GIS compatible format. And this is just a snapshot of water resource information system of India, where for all the, because the water does not follow our this political boundaries. So all natural basins of the, this one like Indus Basin here, this Yarlung, Zangpo, and then this Brahmaputra River Basin here, and then this Luni, and then there are certain basins which are within the state also. There are rivers like Godavari, Ganga. So all this digital database is there, which users can download and utilize for their water source assessment. And then these days, the research focus is now on estimation of hydrological parameters like precipitation, evapotranspiration, discharge, and also the storage, which can be a combination of soil moisture, surface water, and groundwater. If you want to use the surface water, then Saral Altica SWOT. If you want to for the soil moisture, there is dedicated satellites for soil moisture. Then for the full water storage, this is the GRACE gravity-based mission. So the main research focus is on how we can accurately estimate these parameters and how we can reduce the error in these estimates, both in space as well as in the time. Then this is just one example of the global rainfall data. We have this for Brahmaputra Basin, because a lot of catchment area in the upstream, then you have a lot of complex topography here. So how we can estimate this particular rainfall data at sub-hourly time scale, and also at 10-kilometer resolution. Although these data sets are prone for the errors, and it is well-known fact that in the hilly areas, complex topography, the GPM, TRMM, they will underestimate by almost 10 to 20% in many of the cases. So the ground observation plus satellite data is the best way to see such kind of rainfall events. The same is seen in the Kerala 2018, the Western Ghats, where we have the steep topography. So although spatial extent, it is very well captured, but the value was underestimated as high as 41%. So that is why Indian Meteorological Department, they combine the data from the satellite and their interpolation using the gridded data to give you the actual revised value. Same way you can do for your country also. If it is the hilly area, very steep, you have to combine that with your own gauge observation. Then you have this Saral Altica, which gives the water level at very high precision for all the major water bodies. And then you have this remote sensing, which is operationally used for flood mapping. As I told, the clouds will not let you see what is beneath. So that is why we are using the synthetic aperture radar. And why it is able to see? Because it is sending its own electromagnetic radiation, and it is getting specularly reflected away from the sensor. So that is why we get very less return from the satellite. So the water looks black in the radar image. So this is the breach of Kosi at the border of Nepal and India. So it caused very large scale flooding. So you can see cloud free optical data plus radar data from a radar set and also from the TerraSAR, so to generate the long duration flooding. So this all data sets, because we know the topography, we know the rainfall. So we have this flood hazard maps generated by ISRO. So all these long duration flooding from 1990 on has been
Hello.
Hello, Dr. Previ. Seems your internet is not so good.
remote sensing data.
Oh, good. Thank you.
Yeah, so this one for the China, because as I told, remote sensing data is global in nature. So in 2020, we have very heavy flooding in many parts of the China. It was 21 large-scale floods it was observed, which was highest since 1996. So this is one just cloud-free image of the Modis, where this Songhua River province, a lot of flooding has taken place in this particular area. And now these days, because our Southeast Asian countries, they have a lot of cloud cover. So this Copernicus program, freely available Sentinel data is there. So this is for Assam, this is for the Myanmar, North Myanmar. So there was flooding in that particular region. So that can also be downloaded free of cost every 6 to or 12 days to map these flooded areas. Then in the hilly areas, it is very difficult because they are the flash floods. So in the flash flood place, it is difficult to identify this map due to the topographical factor. So post flood case, 2013 in Uttarakhand, we have very heavy rain, this flooding. So in the post image, you can see here the signatures of the flash floods can be easily identified, and then you can calibrate the model. You can know that this area must have received very heavy flash floods or the heavy rainfall, plus the landslides, and then there is some kind of landslide breach. So those kind of signatures can be very easily marked using the satellite data. Then the shifting of the rivers due to the heavy discharge in the alluvial terrain, that can also be mapped. And then this is just a summary how we combine the topographical, meteorological, and land surface data for the hydrological model, including the design flood estimation. So this is one example of Beas River where we use the sub-daily rainfall data and calibrated the model to get the very precise flood peak, and also did the hydrodynamic modeling to simulate that particular area. So if you have good quality rainfall data, good quality topographical data, your accuracy of your simulations will be very high. And then this is the summary of the flood forecasting systems. So the input is we have this meteorological forecast. This is the WRF example when we did this early warning system in Northwest Himalaya, and this is the calibrated hydrological model, and this is the
Oh,
hydrodynamic model, and this is
excuse
the
me,
actual.
doctor. 1 minute
Yes,
left.
yeah. I'm
Thank
finishing.
you.
Yeah. So this is the actual photograph, and this is the simulation. Because many parts in our developing countries, they make infrastructure in the low-lying areas because of the socio-economical and land availability constraint. So they do get flooded each year. And we have this special flood early warning system in the Bhuvan website, where you can see here the recent flood was forecasted well in advance, the flood inundation. And for the global players, we have this European medium range flood forecast, and it is freely available. Anyone can access from hydrological forecast, the meteorological forecast, and the flood risk map at the global time scale. And this is an example of how we evaluate the various forecasted rainfall data for the with the hydrological models. And in Himalayan region, these days we have a lot of problem of the glacier lakes, including India, China, Pakistan, Bhutan, and Nepal. So these glacier lakes tend to breach suddenly, and they can cause heavy flooding in the downstream area. So this can also be monitored using the satellite data. And one last slide on the urban flooding. So many cities in India and Southeast Asia have seen rapid urban growth. So, and their drainage channels are also choked due to the mismanagement of the solid waste. So they tend to increase the flood peak, and also due to the climate change, the rainfall intensities are progressively increasing. So if you have the less drainage path and very heavy rainfall, it causes heavy flooding, flash flooding in the many cities all around the world, including our Southeast Asia and the many developing countries. And this is just a summary. In the future, we will have a dedicated satellite, surface water and ocean topography, which will give the river discharge as an output. And then we have this NASA ISRO mission, L band and S band, which will give us the free data in both the frequencies, which can be used for the flood studies. And then we have this resource at 3A, 3B, just like Sentinel 3A and 3B, which will give us a wider swath and more revisit so that we can precisely estimate the flood area. So with this, I will stop now.
Okay, thank you very much for such an informative presentation. Just one question from our trainees in Zoom chat. Doctor, you can check you can check Zoom chat too. And I
Yeah.
think for limited time, we can respond to one questions, and others trainees can contact doctor after training. The question is, how can we DEM DM 30 meters and 50 meters, and which one is the best for hydro
Yeah.
modeling?
Yeah.
Please.
So this one, if you have the large catchment area like Ganga Basin, Brahmaputra, Indus, in that case, the 30-meter DM is sufficient. But if you have very low relief, the slope is very less. In that case, it is better to have the high resolution, and it is the river-based inundation in the flat area. In that case, it is better to have even better than 15 meters for the hydrological modeling. Otherwise, if it is the dominant hilly area and very less this topographical relief is higher, in that 30 meter is also good. And for the Southeast Asia, I will refer you for the Kato DM, which is available for South Asia, 30 meter. And there is even one more 2 DMs which has come recently. One is from this Alos World DM that was actually generated at 5 meter, but resampled at 30 meter. And one more DM from Copernicus, which was originally made at 12.5 meter and resampled to 30 meter. And they have even removed the forest and topography. So if you remove forest and topography, it is known as FAB DM. So these 2 DMs are the latest one, and traditionally we have this Kato, Aster or Astatine that you can use. But this Alos and Copernicus DM, if you want to start your for the beginners, that is the best DM that we can use now.
Thank you very much for wonderful presentation to